Hello, my name is Alec Tolentino,
And I'm Roland Martinez.
and we will be presenting about activity 2, which is generate a pulse with modulated signal. So pulse with modulation. Pulse with modulation is where an analog signal is sampled at regular intervals and each sample is converted into a pulse with varying width. PWM or pulse width modulation is a way to control analog devices with a digital output. PWM is a great method of controlling the amount of power delivered to a load without dissipating any wasted power. It is used in variety of applications such as to control the speed of a fan, adjust the brightness of LEDs, and for controlling the angle of servo motors. So this figure shows the input message and sampling pulse and with the output PWM signal. Next is duty cycle. When the signal is high, we call it on time. Then to describe the amount of on time, we use the concept of duty cycle. Duty cycle is the term used for the comparison of on versus off. Duty cycle is measured in percentage. The percentage duty cycle specifically describes the percentage of time a digital signal is on over an interval or period. This period is the inverse of the frequency of the waveform. Then if a digital signal spends half of the time on and the other half off, we could say that the digital signal has a duty cycle of 50%. We can see here in this figure and resembles an ideal square wave. If the percentage is higher than 50%, the digital signal spends more time in the high state than the low state, and vice versa if the duty cycle is less than 50%. Then if 100% duty cycle, it could be said that it's the same as setting the voltage to 5 volts, and if 0% duty cycle, it would be the same as grounding the signal. So next is the data sheet and activity results. So the activity procedures is number one, build a pulse width modulator circuit using LTSpice. Video record while doing the activity. Use a software that can capture desktop activity while taking video. You may use the sample circuit shown or create another circuit similar output shown in figure 1. So this is the in figure 2, it shows the circuit that we will be replicating into LTSpice. Step 2 is to take a screenshot of the completed circuit in LTSpice and paste on your lab report. Step 3 is simulate the circuit and show output for the sine wave generator, square wave or pulse generator, and PWM circuit. Step 4 is take a screenshot of the simulated outputs in LTSpice and paste on your lab report. And the last step is to save the LTSpice file and video file for validation. Separate files in Google Drive by folder or by activity. So next is we will be showing our time-lapse video in uh, building the circuits.
Hi there, my name is Roland Martinez, and this is a video demonstration of the Activity 2 in ECE122L, or the Digital Communications Laboratory, Section E02. And the activity is entitled Generate a Pulse Width Modulated Signal using the given circuit in LTSpice. So in this activity, I will show you or walk you through the building and simulation of the given circuit and LTSpice. So let's get right into it. You already seen that I have already simulated the original schematic diagram that is given for this activity, but I observed that the sinusoidal input has no amplitude, or the original sinusoidal input is the DC offset is 4 while the amplitude is 0 and the frequency is 1k, which gives a 0 DC, and no sinusoidal wave is created. So I switch the DC offset to 0 while the amplitude into 4 volts. And another replacement that I did in this schematic diagram is the pulse, which is this voltage input is to be a square wave generator, and the original voltage input here is 8 volts, and you already seen that the simulation result is only a 8 volts of a straight line or DC voltage. So to generate a square wave, I use the parameters for the V initial for the V on 0. T delay is 0.01 microseconds. T rise 0, well, T fall is 0. T on is 0.05 milliseconds. The T period is, or the duty cycle is 0.5 milliseconds, and the cycles that I'm going to simulate is 100 numbers of cycles. So to verify the result of this pulse width modulator circuit, I can now proceed to the simulation or the run button. So to emphasize each sinusoidal or output waveform, I will add a plane for the first plot or first graph. For the sinusoidal input or the modulating signal or Vin, it is a sinusoidal input. Delete this plane. Additional plot plane for the square wave generator, and the output is square wave in blue color. So to further observe the outputs, you can zoom on the plot. Then to verify the capacitor discharge on the diode side or the 1N4148 diode, you can click the probe on the node here on the cap disk label. So we already seen the red line that it has a small width and a larger width, which this will be the limits for the pulse width modulated output signal. So to verify that, we can add another plane for the pulse width modulated signal or the final output of this schematic diagram. So clicking the V out or using the probe, you can see that the modulated signal, to zoom it and see that there is a larger pulse width and which has a larger duty cycle and a small positive high pulse with a lower duty cycle that corresponds to the capacitor discharge for the small length and the or small width and the larger width capacitor discharge on the diode side. So to combine these all outputs, you can rerun the simulation, and I'm going to use a only one plot for all the signal outputs. For the first input, be sinusoidal again. Then for the square wave generator is a square wave that is 4 volts high, same with the sinusoidal wave. But for this square wave generator, it only has a positive side, no negative side, or the polarity is all positive. Then for the capacitive discharge or the capacitor discharge, see that the capacitor discharge is on red line. And lastly is the final output for the pulse width modulated signal. And we can see here that the pulse width modulated signal is varied by the capacitor discharge with respect to the uh, square wave generated signal. So by the way, I also changed the magnitude of the pulse to 4 so that the generated signal can be seen or can be observed more clearly than using an 8 volts of pulse magnitude. So that's the final result of this simulation. Thank you.
Hello, my name is Alec Tolentino, and I will be uh, demonstrating activity 2, which is generate a pulse with modulated signal. Pulse width modulation is where an analog signal is sampled at regular intervals, and each sample is converted into a pulse with varying width. PWM is a great method of controlling the amount of power delivered to a load without dissipating any wasted power. It is used in a variety of applications such as to control the speed of a fan, adjust brightness of LEDs, or for the controlling the angle of servo motors, to name a few. So the procedure is to first build a pulse width modulator circuit using LTSpice. So now I'll be proceeding in building the circuit. So after building a circuit, we now simulate the values for V in, which is the modulating signal, then for V out, the PWM signal, then for node 1 is the pulse carrier. So combining them into one graph, we have the output. So we were able to simulate and get the output waveforms for the circuit in LTSpice.
To continue with the datasheet and activity results, you can see the LTSpice schematic diagram or the circuit using LTSpice of the pulse modulator circuit. Uh, it is shown here that we use the NE555 timer for the pulse generation, and for the modulating signal, we use a sine or signal wave, signal voltage wave with a sine of parameters of 0 magnitude for this offset, for the magnitude of the sine wave, and 1K for the frequency of the sine wave. And the square wave generator will use uh, a voltage source with a pulse of 4 volts of magnitude with the corresponding parameters for the square wave generation. So another part of this pulse modulator circuit is the uh, capacitor discharge, where the discharge from the timer will be converted or rectified uh, in using the 1N4 148 diode, where the generated signal here is a sawtooth, which will be the base of the pulse width modulated signal for the V out. So you can see in the screen the figure where the simulated pulse modulator circuit for the V in is a sinusoidal wave with a 4 volts of amplitude for the positive peak and negative 4 for the negative peak with a frequency of 1 kilohertz. So next is the simulation of the result with the pulse signal using the square wave generator uh, with using the pulse parameters for the original voltage input in VCC. Next is the sawtooth that is generated using the uh, diode from the NE555 timer and resulting into a sawtooth of a small and a big or large tooth, where the PWM signal output is being varied. You can see here that the PWM signal is generated with a duty cycle of around 80% for the first positive or the high state. Then for the uh, corresponding negative cycle of the modulating signal, the pulse with pulses is on low state. Then a positive or high state of about 20% is being shown, then back to the low state and going back to the 80% high state or the positive cycle of the pulse width modulated signal. So to clearly show the pattern for the inputs such as the modulating signal, the square wave signal, the sawtooth signal, and the uh, main objective or the output of this activity, you can see the plot panes for the modulating signal for the green sinusoidal wave on the bottom. Then for the square wave generated signal on the uh, blue colored square wave signals. Then for the sawtooth signal, you can see the red colored sawtooth signal. And for the main output or the PWM signal is the cyan colored generated signal or the V out. So as conclusion for this activity, uh, the analog modulating scheme or the modulation of the pulse width modulation is also a analog signal output. Then the duty cycle is the ratio of the on time or the high state or low state over the high state over the total or average of the high state and low state of the cycle or the positive state on the uh, pulse width modulated signal. Power delivered can be controlled using pulses. So you can see in the graph that we already uh, generated a pulse width modulated signal using the square wave signals and the sawtooth signal. And there are three variation of the PWM, which is the leading edge, where the leading edge uh, is the leading edge is the technique where the signal leads edge is fixed and the trailing edge is modulated. Then for the edge modulation, it is a technique where the signal's lead edge is modulated and the trailing edge is kept fixed. Then for the pulse center two edge modulation, it is a technique where the pulses or the pulse center is fixed and both edges of the pulses are modulated. So it is already shown in the introduction or the discussion slides, the three types of variation of the PWM. Aside from the variation, we also have the application of the pulse width modulation, where pulse width modulation is a technique used in telecommunication for encoding purposes, and it also helps in voltage regulation and therefore is used to control speeds of motors, as Mr. Alec Tolentino said. And PWM technique controls the fan speed, fan inside a CPU computer, or thereby successfully dissipating the heat. And PWM is used in audio, video, and amplifiers. So for this activity, we focus on the uh, application on telecommunication for encoding purposes. So the PWM frequency is high and switching losses are considerably high. And other observation for this activity is that the bandwidth depends on the rise time of the pulse, and the instantaneous transmitter power varies with the amplitude and the width of the pulses. And some system or the system complexity and noise interference for the pulse width modulator circuit are low, which result in the low cost in building this type of circuits. And similar with the frequency modulation, uh, the complexity and noise is low. And the frequency of the pulse width modulated signal determines the how fast a PWM completes a period, as discussed by Mr. Alec Tolentino. And that concludes our presentation or for the activity 2. Thank you.